we have a flat surface. The car is making a left-hand turn, and we're being asked about the maximum speed the car can go through the turn, negotiate the turn without sliding off. And we're asked to solve for this kind of maximum speed in terms of Rm and mu and fundamental constants. A good starting place for any dynamics problem is to draw a free body diagram. I've done that here. I've used a traditional coordinate system in the y direction with up positive and down negative, but I have flipped my x-axis. You don't have to do that. The reason I wanted to call left positive is because based on the orientation of the car taking a left-hand turn, left is radially inward and typically just gives you fewer negative signs to deal with when I call radially inward positive. You don't have to do that. The problem won't be wrong if you kind of flip that. You just have to keep track of more negative signs. It shows up right here when I say that the frictional force, which is positive, is equal to my leftover force. When moving in a circle, we call these leftover forces centripetal forces, center-seeking forces, not to be confused with the word centrifugal or center-fleeing forces, right? Those are fictitious forces. So these two forces, so the leftover force is caused from the only horizontal force, in this case, friction. I haven't put a subscript here. I have mu times the normal force. This is given to you on your equation sheets, but the question I have for you should I write static or kinetic as my subscript? If we were given two different numbers for the static and kinetic coefficients of friction, which one should I use? What do you think? Yeah, kinetic. A lot of people instinctively go to the kinetic coefficient of friction because the car is moving. But the key here is that the car is not sliding. The surface of the tire, when in contact with the road, is not sliding yet. If it was drifting through the turn, then we would say, yeah, we're going to use the kinetic coefficient of friction. But when the car rotates, the tire patch that's in contact with the road is not sliding past the road. Yes, the tire is moving, but that patch, at the instant it touches the ground, has a velocity of 0 relative to the road surface. So they're not sliding. I am going to use the coefficient of static friction, and that's important on this kind of a problem. Are there questions on that? Okay, so now I set this up equal to the centripetal force. By the way, don't let this piece be confusing for you, right? All this is Newton's second law. So I'm just saying that F is equal to ma. We used to call this F net, but when we're dealing with things moving in circles, we call it a centripetal force. And a centripetal acceleration is v squared over r. A sub c is equal to v squared over r is given to you, and we just substituted that in. This isn't something new. This is just Newton's second law applied to things that are moving in uniform circles. So I have this expression of mu static times the normal force is equal to mv squared over r. I'm not permitted to leave my expression in terms of the normal force, so I'm going to then need to make this substitution in for normal force. This becomes mu static mg is equal to mv squared over r. We can see that the mass of the car does not affect the speed with which you can negotiate the turn. So that's good, it cancels out, and I can solve this expression for v. I get mu static times the radius is equal to v squared, and then I can take the square root of both sides. That becomes the maximum value. Remember that the coefficient of static friction is variable, right? So it's the weird one where the kinetic coefficient of friction is just one number, and the coefficient of static friction goes anywhere between 0 and some maximum value. So this is kind of a sliding scale. It can be 0 if you're not moving, right? So friction doesn't start to act until there's a tendency to move in one direction, and then this reaches its maximum value. Are there any questions on how we arrived here? Oh, thank you. I forgot gravity. So I left g out when I multiplied both sides by r. Thank you for noticing that. So notice that if it happened on in a higher gravitational field, you'd be able to go through the turn faster because of the contact pressure consequence between the tires and the road. All right, any questions on this? Okay, here's what I'd like to do. In the application of this problem where you go around a banked turn, which you'll see in the Physics C question banks. This is, NASCAR super speedways all have bank turns, and what they do is they introduce into the problem a component of the normal force that's helping you through the turn. I don't know if you guys have ever watched velodrome, which is like a cycling sport. I only see it from time to time in the Olympics. But if the cyclists wear these weird helmets, if you ever see cyclists and they look like the guys on the Death Star who go, like they're getting ready to shoot, and they have these huge, every time I watch Star Wars, I'm like, that's a velodrome helmet that they grab for that scene. Anyway, the velodrome helmet is very, the shape factor is advantageous for aerodynamics. It's got this like long tail to it. And they go around a bank turn insanely fast. The thinking is, if the bank angle here, theta, increases to 90 degrees, you could effectively go through the turn without friction as fast as possible before the material failed, right? So it's until you crash through the bank and the wall in this case, you could keep increasing your speed, which would be ridiculous, because then you would have to endure these, high G forces. But in the bank turn, this is typically not 90 degrees, but you get more of an advantage the higher the bank angle, the larger the angle theta is. Your instinct when you see this sketch is to rotate the coordinate axis and to think about it as an object on an inclined plane, which it is not. The reason that we rotated the coordinate axis on these problems was because we were interested in movement up and down the parallel plane, parallel to the surface of the incline. That's going to be bad if the car is sliding up the incline. If you are driving this car and you're going up the bank like this, you're gonna hit the wall on the other side of the turn. That's not good. The thinking is, when you're answering a similar question to what we saw here, a circular motion question, we're not going to rotate the coordinate axis. We're not going to discuss parallel and perpendicular planes, because we are imagining a circular path with the center of the circle here, a radius r, and the position, the vertical position of the vehicle going around the turn is not going up or down the incline. It's not changing. So we are not going to rotate the coordinate axis. We're going to leave the coordinate axis here traditionally like this. By the way, we could have done this on an inclined plane problem. It would have just made it a lot harder to solve. We rotated the coordinate axis to make it easier for us. But now I'm going to have a traditional x and y axis. I'm going to label them here positive x. I'm actually going to call this one positive x because that's radially inward, and I'll call to the right negative x. So I'm again making a similar convention adjustment to what I did on the flat problem that we did. Okay, so this introduces some interesting adjustments. Let's go ahead and identify the forces acting on the car. Cam, what's at least one force acting on the car? Okay, so that's the consequence, that's the leftover force. So we're not going to draw that on a free body diagram. Let's try it one more time. The normal force. And what's the direction of the normal force acting on the car? Good, perpendicular to the plane. Normal to the plane, that's where that word comes from. So unlike the last problem where the normal force was conveniently aligned with the y-axis, we're now going to see that the normal force is directed perpendicular to the plane. I'm going to abbreviate it, instead of F with a subscript N, in this case, I'm just going to call it capital N. And the reason that I'm going to do that is that I have to eventually resolve the normal force vector into its x and y components, and so there's going to be a lot of subscripts. So I'm just going to go with a capital N, but if you prefer, the more traditional F with the subscript N, of course, that's acceptable. Other forces that we need to identify. Austin? Friction. Good. It's a tough question. What's the direction of the frictional force? I want you guys to answer that question and turn to the person sitting next to you. 10 seconds. Argue about what the right direction for the frictional force is. All right, let's check in. Daniel, what do you think the direction of the frictional force is in this problem?
Let's say negative x.
Negative x. Positive x. So along the x-axis in this direction like that.
Not.
Okay, down the incline? or up the incline? Down the incline, good. So think of this problem right here. Everybody was comfortable with the fact that friction was acting radially inward. You turn the wheels of the car, and that's the only thing that's pulling you towards the center of the circle. Now we're just lifting the whole thing up a bit. It wouldn't suddenly change and friction is now radially outward. That's not how it works. So friction is down the incline. Notice that I'm going to draw it in here and label that with an F. Again, now, if we haven't rotated the coordinate axis, we now have a friction. We're going to have friction components and a normal force component. There's at least one thing that we're missing. What is it, Stephen? Yeah, gravity. The weight vector is directed radially downward. I'll draw that in green. And so that's straight down to the negative y-axis. I'm going to label that with a capital W so that we have three forces acting on the car that all have one letter to represent them. Okay, I'm going to take Jess's question.
Are we looking at the back of the car?
We are. Again, in a similar way, it's the same problem here, and we're basically rotating the whole thing up so it's going around a bank turn. Yeah. Okay, what I'd like you guys to do is to take 3 minutes and generate dynamics equations that represent the movement of the car through the bank turn. Ready to go. Okay, I've written some starting points. It's going to get more complex here shortly when we try to resolve these components, these vectors of their components. But you should be able to look at the free body diagram and say, okay, the y component of that normal force is in the upper direction, so I'm going to write that as n sub y. I know that the weight vector is in the negative direction. I don't even have to resolve it. All of it is in the negative y direction, so I'm going to subtract the weight. And the y component of the frictional force, when I resolve it into its x and y components, since it'll be in the third quadrant, the y component is negative, and when I add them all up, they're going to be equal to 0, and we know that because the system is non-accelerated in the vertical plane. Are there any questions on that starting equation here? In the x direction, we know there's a leftover force. There has to be if the car is turning. That, at the end of the day, is your proof. The car is accelerated, even though the speedometer isn't changing, the direction is changing, therefore the car is accelerated. Again, the x component of the frictional force, once I resolve that into its components, plus the x component of the normal force, which is also positive, radially inward. Both of those add up together. The weight has nothing to do with the x direction forces, and I call that my leftover force or my centrifugal force. Are there any questions on either of those two starting equations in the x and y plane? Okay, here's where it gets interesting. If this angle is theta right here, what can I say about the angle that the frictional force makes with the x-axis? Theta or not theta? Okay, this is also theta. These are alternate interior angles. If you think of, if I extend this line here, right, this angle here and this angle are the same. So the frictional force makes the angle theta with the x-axis. That means when I resolve the frictional force into its x and y components, I'm going to use my traditional trigonometric components, cosine for x and sine for y. We've done the trig before, you guys have seen it. How about the normal force? Does the normal force make the angle theta with the x-axis? Does the normal force make the angle theta with the y-axis? It does. The normal force and the frictional force are perpendicular to each other. That means they add up to 90 degrees. So, theta plus some intermediate angle, which I'll just call beta, when I add beta and theta together, I get 90. We know that the x-axis and the y-axis are at 90 degrees to each other, and so therefore, when I subtract 90 from beta, I'm left with the original angle theta. However, I'm referencing the y-axis now, so I have to pay attention to my vector resolution. I'm going to give you guys 3 minutes. to expand each one of those initial dynamics equations into their component parts using trig. Ready, go. Did you crush this already? Once you've done that, I want you to solve for the final expression Vmax. So what's the maximum speed this driver can negotiate the turn without sliding up the incline and crashing? I was like, you're the only one that's like, I discreetly went over there and hit it. And I didn't see that. And that's the whole point. That's discreet. You have no idea, which doesn't change like what you guys are doing, and it shouldn't change the way I was taught. You should have put some sort of back end light. But I like not only the visuals doing the flashing, but I like being able to look up at the camera and it's the same with the light. Okay, so, I think a good way of thinking about this is that you're just going to flip-flop, x is usually cosine and y is usually sine if you reference the x-axis with the angle theta. And if you don't, if you reference the y-axis, you have to flip them. We talked about that last year. If I were to kind of show you the geometry there, it would take 5 minutes, but I'm going to assume that you're okay. So x is f cosine theta because I'm referencing the x-axis with the frictional force angle. The normal force, though, for the x component is now sine theta because I'm referencing the y-axis, and then I set that equal to mv squared over r, just like I did in the non-bank turn problem. Now I get the y component, I'm referencing the y-axis. Normally, if I'm dealing with a y component, I'm going to use sine, but I have to flip it to cosine because I've referenced the y-axis with the angle theta, minus the weight vector, unresolved because all of it is straight down, and then finally, the y component of the frictional force is f sine theta. Are there any questions on how I got those two expressions? Now you're going to see that I'm going to need to have something for normal force. We have the same problem that we had over here in the unbanked problem. The normal force is not an acceptable variable to have in our final expression. So I'm going to end up solving this for the normal force and then substituting it into here and solving for v. Finish that problem algebraically. I'll just give you guys a couple of minutes to finish it up. Okay, it does get a little messy algebraically. This is just messy algebra. I developed an expression for n here. Notice that the normal force shows up in two places in this y equation. There's also a frictional component in the y equation, which is normal force dependent, right? So mu static times the normal force. I have two terms that have the normal force in it. So I got rid of mg, I moved that to the right, factored out the normal force, I'm left with cosine theta minus mu static sine theta is equal to mg. Then I divide both sides by that thing and don't drop my parentheses. And then on the left-hand side, I get the normal force showing up in two terms. And I could substitute them both in, but I just said, hey man, why don't I just factor out the n of both terms? And that way I only have to substitute it once. It'll get less messy that way. And so I factor the n out, and I'm left with mu static r cosine theta in the numerator plus r sine theta all over m. I just kind of simplified that fraction, factored out the n. Then I made the substitution. So even though I visually kind of represented it up here, I decided against that, made the substitution over here, and I get mg over cosine theta minus mu static sine theta. The m's cancel out, and I just distributed the g to both of the terms in the numerator, and I have that in the denominator to take the square root of both sides, and I'm done. Are there questions on that? Shani?
Why did you develop an expression for n based on the y components rather than just taking the weight vector and like doing the theta, like the thing that you would normally do for something such as
So you're saying why didn't we why don't we just rotate the coordinate axis like it was on an inclined plane? I think because I think what you're saying is if we had rotated the coordinate axis, we wouldn't have had to resolve the frictional force and the normal force. Is that your thinking?
No, just like instead of doing n equals mg over cosine theta minus mu static
Yeah.
sine theta, why didn't you just do it in terms of the weight vector for just for the normal force and do it with like the mu instead?
Yeah, but if so why did I like break this? Why didn't
Well, because I just made the normal force like mg cosine theta and then put that in for all of my normal forces.
Oh, you could have done that. Do you think it would have?
And I did not get the same answer.
Okay. Well then maybe
I don't know if I think
there's an algebra mistake somewhere, or maybe I made one. But I'll double check this one. But I'm pretty sure that's consistent with what you should get for a VMAX type question. All right, I'm going to stop there.